How to integrate photonic qubit control. Imagine a tiny light switch that can turn quantum bits of light on and off with perfect precision. That's what controlling photonic qubits is all about. It's a key step in making quantum computers work smoothly. So, how do scientists do it? Let's find out. The process starts with creating single photons or pairs of entangled photons. They often use special materials like nonlinear optical waveguides or solid-state emitters, such as quantum dots built right into the chip. These sources generate photons with specific properties needed for quantum tasks. Once created, the photons travel through tiny channels called waveguides, which are etched into the chip. These waveguides are like optical highways, guiding the photons to different parts of the circuit. Next, the photons encounter components like beam splitters. These devices allow photons to interfere with each other, which is essential for performing quantum logic operations. Think of beam splitters as light mixers that help photons interact in controlled ways. Then, there are phase shifters. These are devices that change the relative phase of the photon's wave. Adjusting the phase is how you control the qubit state, like tuning a radio to the right station. All these elements are combined on a single photonic integrated circuit, which makes the system compact and stable. The goal is to minimize optical losses because photons cannot be amplified without losing their quantum information. To do this, engineers use low-loss materials and precise fabrication techniques. Control over the photonic qubits is often achieved by electrically tuning the phase shifters or thermo-optic elements embedded in the chip. These allow real-time adjustments, making the system flexible and responsive. For more complex operations, multiple photonic qubits are controlled across different zones or channels on the chip. Recent advances include multizone control, where photons are transported and manipulated coherently in different parts of the integrated system. This helps build scalable quantum processors. Hybrid integration is another important strategy. It involves combining photonic components with other quantum systems like superconducting qubits or spin-based qubits. This requires careful engineering to manage different operating temperatures and signals, often using microwave-to-optical transducers to connect the systems. Practical uses of integrated photonic qubit control include linear optical quantum computing, where photons are used to perform calculations, and measurement-based quantum computing with photonic cluster states. Photonic qubits are also vital in quantum communication, especially in quantum key distribution, where they carry secure information over optical fibers. In short, controlling photonic qubits involves assembling tiny, precise components on a chip to generate, manipulate, and measure quantum light states. This technology makes scalable quantum systems possible and opens the door to hybrid quantum architectures. It's a fascinating step forward in the world of quantum information.